Okay, so yes, as Jörg said, the theme of this talk is going to be on avalanche impact pressures. And obviously, this is one of the classical and most important topics that you have in avalanche dynamics. This affects the calculation of avalanche impact pressures, affects how you do avalanche hazard mapping, it affects how you design defense structures. It's also extremely important for protective forests. It is clearly one of the major themes. Now, my title is sort of interesting because I say problems. I could have began with a problem, so that's sort of interesting. What problems in plural do we have? And then I do something out here and I say existing theories, right? Now, that's also sort of an interesting question because do you have more than one theory? And if so, how do these theories of avalanche impact pressure differ from one another? That's sort of an interesting question, okay? So that's basically, I want to talk about these problems and these different theories and some of the problems with these theories. I would like to begin in a funny place. You see all these objects that I have up here, for example, these rocks. Avalanche impact, or the problem of impact, is one of the big problems, not only in snow science, it's also in rockfall science, and in fact all natural hazards. It's the reason why you have natural hazards, okay? And what is interesting is that if you go to the rockfall community, what you find is that the way the rockfall community treats impact is somewhat different from the way the avalanche community treats it. This is somewhat funny, okay? Or perhaps they don't treat them, or they treat them the same, but you just don't know it, okay? So this is sort of interesting. For example, For example, if I were a rockfall engineer and I was given the task of designing a rockfall net, okay? Now think about an avalanche engineer also has the problem of designing an impact of a structure. A rockfall engineer would almost immediately invoke the work energy theorem. And the work energy theorem says that the change in the kinetic energy is equal to the work done during the braking process, which is equal to the impact force, which is equal and opposite to the force acting on the object, which is stopping it down, times this braking distance, okay? So it's the product of two things. And what the engineer would do is he would then calculate, he would tell the people he wanted a net with a particular braking distance, and as soon as he would define that braking distance, he could then calculate the force, right? He would divide the change in the kinetic energy by the braking distance. So this formula you shouldn't like at all. And the reason why you shouldn't like it at all is because it's divided by the braking distance. And you see immediately if this thing goes to zero, this force goes to infinite. Now Stefan Marger is now really worried because he doesn't want infinite forces on his object. But this is true, this is not a fake story, right? If this rock comes in here and the engineer decides to make the braking distance extremely small, then the pressures or the impact forces are going to go up, and they're going to go up a lot, okay? So this is not fake news. This is very, 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 very important. And it's the governing principle in rockfall analysis, okay? Now there's certain things that you have to be aware of now, right? If I were to take this rock, and we make these 2 tons when we throw them, and I were just to let it fall down on the ground, a physicist would say, well, I've solved that problem. What happens is it falls down on the ground and then it bounces back, and you have a restitution coefficient, or you have a Stoss coefficient, which tells you how much energy is used. So if you say the restitution coefficient is 0, you have a plastic impact. Now we're back to Bruno Salm, Jörg and I, okay? Now the thing is that the physicist would say, well, I've solved this problem. It's easy. All I do is I give you a restitution coefficient. So a piece of nice aluminum like this, it's probably pretty high. But then the engineer comes and says, well, wait a minute, I want to know the force. I don't want to know how high it bounces back. I don't care about anything else, right? I want to know the force. And as soon as you say, I want to know the force, it's a game changer, right? Now, the reason why it's a game changer is because, well, look, this rock, if I drop it like this on the ground, it has a different braking distance when it hits the ground, and I'm not going to drop it because I'll get into trouble with Martin Gentner because it will probably break something down there. Then if I drop the rock say like this. And this tells you something that's really, really important. This tells you that the problem of avalanche impact pressures has a lot to do with the configuration and the sizes and the shapes of these objects, right? So if I drop it like this, I measure one force. I drop it like this, I measure a completely different force. And we'd be aware that the problem would have the same restitution coefficient, okay? So this is very important, that you're going to get large changes, large variations in what you see and what you measure dependent upon very small things. The other thing that to notice is that the braking distance, d, is a distance. It's not a strain. It doesn't tell you anything about the different processes which are happening during the braking process. What is happening when I break the floor? Just a distance. In fact, it's a combination of many, many different things. It could be elastic, it could be plastic. It could be, for example, in a rockfall net, what happens is you use the friction between the elements to stop the rock. So you have many, many different processes that can contribute to the braking distance. So the braking distance is sort of nice in a way. It's dangerous because if its small forces go up, but it's nice in that you don't have to attribute it to one particular process. Okay? So that's the first lesson. And for Jörg, I say the work energy theorem is the most important theorem in all of snow science because it tells you what happens when you fall off your skis, right? It's because snow is soft, and when you fall off that you have a large braking distance that you don't get hurt, right? This is what you're invoking. Every time you fall off your skis and you fall into a soft snow cover, what you're doing is really using the work energy theorem. If you were skiing on ice, the braking distances would be very, very small, and you would hurt yourself a lot. Okay? So that's the first part. And now we want to get to snow. And this is a snowball. So I said, how do you calculate the impact force? Right? I could throw it against the wall, and I do this for Jörg because Jörg and Salm, and it goes back about 20 years. I'm not going to throw it against the wall. I'm going to pretend. So what happens is if I were to calculate, I could very easily calculate what the change in the kinetic energy is. It would go from the speed that I throw it to 0. Okay? It's very easy to calculate the change in momentum. By the way, where does the momentum go? You don't destroy it. It goes into the wall. It's also very important. You don't destroy momentum. It goes somewhere. We're going to see what that means in a second. But how do you calculate that? Well, what you do is the engineer, or whoever it is, will assume that the braking distance is the diameter of the snowball. And he'll say that the snowball breaks in that distance, right? And then he'll use the same work energy theorem. I know the change in the kinetic energy. I know now my braking distance, and I can then calculate what the impact force is. Another way of doing it would be to say, well, I know what this distance is, and I know what my mean velocity is over this time, and I could calculate how long the impact lasts. Okay? So you either need the braking distance, or you need the time of the impact to calculate what the force is. And be aware you can make a lot of mistakes. There are experts in Birmensdorf, and even Jörg doesn't know this one. These experts argue an awful lot about what is the braking time? I assume a mean deceleration as the snowball goes from one side to the next. Well, that doesn't have to be true. I could just have a deceleration that goes up and then it goes down, or one that starts off slowly and goes down. And what that means is that the force that you calculate is going to change. It can be a factor 2 or 3 higher than the mean over the same braking distance. Gives you another idea of how difficult it is for a very simple problem to calculate what an impact pressure is. Okay? Another thing, and now we begin to talk about methods, is we have to talk about Hollywood a little bit, right? Because Hollywood makes all these wonderful films. You see these films and things coming down, catastrophe, video games, Brad Pitt, Angelina Jolie. What's happening there? Well, you can do an awful lot just with the restitution coefficient. You can calculate what an avalanche looks like when it hits an object. But the question is what is the braking distance, right? And that needs a little bit more detail. So you always need a little bit more detail to calculate something that looks realistic, and you could have, by making a very small mistake, you could have a very large mistake in your impact forces. Where we encounter this all the time is, for example, in rockfall, because what we do is we calculate these wonderful motions, trajectories of the rocks, and they land up in the right place. But as soon as an engineer comes, or as I say, Alex says, well, what is the force on my tree? What is the force on my snow shed? That's a game changer. We have to ask, what are the braking distances? And that is completely different for a tree than in a concrete gallery or a concrete rockfall shed. And that's why it becomes a very, very difficult problem. Okay? We have to get to the snow problem. And because we're here, the first thing to realize is that when I say snow, everybody's going to think of something else, right? And I just wanted to say that you should keep in mind that snow is going to come in all different forms, and at times it's going to be very hard, especially avalanche snow, right? And you can even have a lot of mud and woody debris. Just think about what that woody debris does in stiffening up and making the braking distances smaller, or how this compacted material, when it hits an object, what the braking distances are going to be. I'm trying to indoctrinate you into thinking, if someone says, I want to know the braking distance, that you immediately think about, or I want to know the impact force, that you immediately begin to think about what kind of snow will have what kind of braking distance. All right? So now we're going to do the first avalanche problem. And the first avalanche problem is that we have this avalanche. Looks like this. Phi is for flowing, P is for powder. Gamma is for the claws, the splashing, right? We're only going to talk about the core right now. And you can imagine this core of this avalanche being what you want. It can be very dense, it can be very, very dilute, it can be very dispersed, and it's going to hit a rigid wall. S, sigma, is for snow cover, because you add it to the snow, right? Now, what we're going to do is we're going to have the avalanche come in, and it's going to hit this rigid object. And what it's going to do, it's going to stop, right? Okay, and we're going to do something for the first part of the analysis, which is to make sure that there's no deflection. That what happens when the avalanche hits the wall, it backs up, and we're not going to, and the mass on the sides will just continue flowing. In about 5 minutes, we're going to stop. We're not going to carry through with that assumption. We're going to change the boundary conditions a little bit to see what happens when we have deflection, which is a much more realistic problem. Okay, so that's the. I think I have a nice. This is something that Chris Pielmeyer sent me, so you can imagine an avalanche arm aiming at a house and then hitting it directly, and then you get this backup pressure. And remember, impact, equal and opposite reactions. Here you have a case where the force was enough to stop the avalanche, right? Like it also happens that it doesn't break everything, it doesn't destroy everything, okay? So how do you do this? How do you solve this problem? Well, it's pretty easy. I have a set of mass coming in. It's moving at a certain velocity. You give me the time period, a delta t. If Marin tells me I want to have an avalanche with 10 meters per second and I want to take a delta t of 0.1 second, then the length of this thing is 1 meter, okay? Then what happens? Well, this 1 meter gets compacted up here in this zone, okay? And what we have is a what? This blue thing. This blue thing turns out to be more important than you think. You have a boundary that is separating the moving mass and the stopped mass. This is not a wave, right? It's a boundary. It has no mass, right? And this and as the mass is coming in, what is happening is that this stopped mass here is growing larger and larger, okay? So it's coming in at 10 meters per second, 5 meters per second, 30 meters per second. It's all piling up. I call this omega, this region here, because it looks like it's being squished. I call this one C because it looks like it's compacting, right? And it's this front is moving out. So where's the braking distance? You have to know the braking distance. It's all I want Steph and Margaret to learn. You have to know the braking distance. The braking distance starts here and it ends up here. And if you wanted to know what it is, then what you could do is you could say it's simply the center of mass, the change in the center of mass, right, between these two. And this front here, the speed of this front is defined by the compactability of the snow. So we're cheating. I'm telling you that the snow, when it comes in, is going to compact to a certain density. When you measure this density and you go out into the field, it's typically about 500, or could even be more, 550 kilos per cubic. So this is not your typical snow. It's very hard stuff, right? Okay, that's all you do. Note that all of the momentum of this packet of mass that hits the wall gets transferred to the wall and then eventually into the ground, right? All of the mass, all of the momentum of the avalanche coming in is taken up by the wall and goes to the ground, and all of the energy is dissipated as heat. No elasticity, nothing happening, okay? So now what you do is you just invoke the work-energy theorem, which is trivial, right? Instead of writing the force, now we're going to write the pressure. We divide by a mass, change in kinetic energy divided by this thing, the braking distance, and you get a formula that looks like this. All right? So what is this formula? Well, you shouldn't like this formula because this formula has a denominator. Nobody likes denominators because the denominators can go to zero, and when they go to zeros, the forces go up. And you see that when the densities are equal, 1 minus 1, and the denominator blows up. So what we're saying is that if this mass that is coming in cannot deform, it can't compact, it acts like a infinitely rigid mass. It's infinitely hard, right? In order to calculate, and then the force is natürlich, the force is of course then infinite. So you need this braking distance, okay? So you also see that as this thing gets to be close to 1 and very large, that this braking distance, or the force will then get very large. So if I were to plot what the avalanche density is, according to this impact pressure, what you would see is that it goes up and then it goes to this, it explodes. It explodes. Okay? This is why things are so difficult for us, because we might be in regions here where you're on a very, very steep incline. Now, another way of thinking about this is mathematically, okay? And this function here is the product, is a product between two things. It's a product between a v squared and something in the denominator, something that is 1 over the braking distance, right? So you can have regimes that are dominated by this v squared. The avalanche will come in and everything is fine, and you see these long periods. Here's a one for a snowball. It goes up, and then all of a sudden, as the inverse product, the braking distance, begins to dominate the problem, what I'm saying is that the mass is getting harder and harder and harder, your force is going to go up. It's going to go up and it's going to explode, all right? So in answer to what the subtitle of this colloquium was, if you want to make a snowball that hurts, and this is what you continuously do, is you compress it. What you're trying to do every time you compact the snowball is that you're trying to move this density closer and closer to a point, right, where you're getting close to the compaction density. And if you could compact it to this point, then the force of the impact would be very, very large. It's difficult to do that, right? So that's how you make a snowball that hurts. Okay? And here for Stefan, just to make him nervous a little bit, for this is 10 meters per second and this is 30 kilopascal. You see that there's a lot of possibilities that you can have a much higher impact pressure than the 30 kilopascals. There's reasons why you don't, why we're safe. But this is just to explain that you can have very high forces. It's not the problem that you have very low force. It's the problem of why don't you have high forces on these objects that are hit by avalanches. Okay? Yeah, another thing is that if you wanted to take if you wanted to calculate this pressure coefficient, the Swiss guidelines use pressure coefficients, and they're 1 for a thin object and they're 2 for a wide object. What this is in the framework of the work-energy theorem It's the distance of the mass that is coming in with respect to the breaking distance. Right? So if this mass comes in and it breaks in that amount of distance, then you have a pressure coefficient of 1. I think that's rather sensible. If you have a mass of this length coming in and it breaks in half the distance, then this thing goes up to 2, for example. But it can go up higher. This much mass coming in, breaking in this distance, then this coefficient then becomes very, very large. Okay. Let's talk about some problems. And problems with shockwave theories. There was a lot of work done in the early 2000s where they calculated exactly this problem. And this problem was, and it's exactly the same setup, you have a mass that comes in, and you have a mass that piles up. This mass has 0 velocity, and you have a wave. Why don't I like the word wave? You have a wave that moves back. Well, what is a wave? A wave is a transport of energy, right? And this is important. If I take this hammer, and this is why I have this hammer, and I hit this thing, I should make it sound a little bit nicer, huh? Or it doesn't even sound, I hit it, I create an elastic wave in this thing, right? Now this elastic wave is propagating back and forth. And what is this elastic wave? Well, it's strain energy that's moving back and forth in the thing, in the object. Now this strain energy, the speed of the strain energy is given by the elasticity and the density of the object. Also note that when I hit this thing like this, the wave doesn't stop. It just goes on forever. If it was purely elastic, it would continue moving all the time. Now that's not the case that we have here. When the avalanche comes in and it impacts, if the avalanche doesn't have any velocity anymore, this wave stops. It stops. It doesn't have any independent velocity from the speed of the avalanche coming in, okay? So there's a big difference. That's why I don't like the word shockwave, because it's not a shockwave. And very clearly, the origins of this theory were based on treating it as an elastic problem, treating it as a jet of water that hits the wall and then moves back, okay? Now, these are the stated mass balance and momentum balance of this theory. This is what you read. Now, you should be indoctrinated enough to realize instantaneously that these formulas are wrong. If you take the momentum equation, right, this part here is the mass coming in. This is the speed, right? So you multiply the mass times the velocity or the speed, and then you get the change in force here. This would be the force. Well, if you look at this formula, just look at it. I told you if you want to calculate what the impact pressure of a snowball is, you have to know the breaking distance. You have to know the time that it requires to change the momentum. In other words, there's nothing here in the denominator. No, that's crazy. You can't do that. Then you think, well, wait a minute, that's just all mathematical tricks, right? Well, you have something up here, right? You have this mass times this wave speed. Well, be careful. There is no mass moving with this speed. This is just bookkeeping. It's just a boundary that's moving back. It's just it's just a piece of information that we have between the mass that is coming in and the mass that is staying still. There is no mass. You can't multiply these two together, right? That's a problem. And where that really, really shows up in these things is in the following. When you begin to put numbers into this theory about this wave speed, right? This wave speed is given by the amount of mass and the speed of the mass and the compaction, right? If you put numbers into this, what you find is that the speed of the wave coming back is faster than the wave going in. Bad news. Bad news, right? Can't do that, right? And you see very, very clearly what they got mixed up here. What happened was they treated it like a jet of water that impacts a wall. So what happens is that the jet of water comes in and it hits the wall and then is reflected backwards. And if this area here is smaller in the reflection, then you're going to get a higher speed. But that has nothing to do with the problem at hand. That has nothing to do with avalanche, with a pileup of an avalanche impact, especially a very, very slow avalanche, okay? So what you calculate are these braking distances. So by invoking the work energy theorem, what you find is that you get negative braking distances, right? Maybe Brad Pitt can somehow imagine negative braking distances, but I haven't been able to do it yet, right? This is Hollywood. Doesn't exist, right? Okay, this is a big problem. This is one of the reasons why I wanted to have this colloquium, because I just don't understand why people haven't stated this before. Now, I told you that we were going to start talking about some real problems. Instead of having this avalanche just come in and pile up on the wall, let's make it a little bit more realistic. This is an avalanche in 2007. This distance is about 1 meter. And they were very, very careful, so they had an avalanche come down. It impacted the structure. It built up a wedge. Okay? The wedge angle was about here. It was about 50 degrees. It's about 1 meter here. Okay? This is a picture of validation that thankfully Stefan dug up for me. This wall here is about 3.5 meters wide. Okay? This angle here is a little bit sharper. Okay? But you see very clearly that what happens when an avalanche hits a wall, that it piles up some of the mass and the other mass moves to the side. Okay? So let's see what happens when we invoke the work energy theorem on trying to figure out at least what, oh yeah, I almost forgot the trees, sorry, Peter, right? What you see is these wedges. When you begin looking for them, they start appearing everywhere. It's very funny. For example, here on the tree, right? You see a nice little tree, and when you look from the top, then you also see these wedges. You can even see them on very thin structures. This is from a snowblower, right? And you see this little portion here because the snowblower throws it up a certain distance, and you see these wedges here. So begin looking for these things because they're all over the place, right? Now, the way that we're going to do this is we're going to pretend that we know how this wedge builds up, right? Mark is in the back, right? When we make jokes because we use finger language and a lot of hand waving in our discussions. In the past problems, we had this wave, this compaction boundary moving back up in a line. Now what we have is this compaction moving up in the form of a triangle. This is our symbol for Spitzenforschung, right? It goes up like this, cutting edge research, right? This is a joke, right? So this is what we're doing here. We're doing cutting edge research, right? It goes up and this angle changes all the time, all right? Now you could say, well, okay, have you ever measured that? Have you ever seen it? No. A lot of you see me working around with an old guy, and he said to me, Perry, I saw them build the pyramids. And when they built the pyramids, they didn't do it like that. They built these things, they had a constant angle, and then they did a layer and another layer and another layer. So there's a lot of different ways that you can build up this wedge, and they turn out to be very, very important. So I'm not going to pretend I don't know it, but let's pretend that let's assume that we know it, right? So we say the avalanche is coming, and over time it's going to build up this wedge, all right? Note that no mass is going to get piled up here, and more mass is going to get piled up. At least we have some visual confirmation that that's the case. So what you do is you do the work energy theorem again, but instead of doing it such that over the whole width of the obstacle, what you can do is you do it in little segments, and you see that every place on the wedge you're going to have a different force because the pileup and these speeds are going to be different. Basically what I'm saying is the braking distance at every place here is going to be different. Now you think, well, this guy is going crazy. What is he doing? Why is that important? Well, it turns out to be very important. Because what you see, if you have the distance and this is about 60 centimeters, which is the width of the pylon in validation, you see that you're going to get, when you assume something like that, you're going to have a large change in forces over a very small width. Be careful what you measure. Now, what also happens is that if you do things like this, you have geometries that are extremely complicated, you're going to get into trouble. All of these edges, all of these little zones where you can compact things, affect what the breaking distance is, and therefore it affects what the impact pressure is. It makes it very, very difficult to interpret what you're measuring. And you think, well, what are you even saying that? Well, we do a lot of this in rockfall. Why do you think we use these objects? Because what we do with these objects is we try to avoid, I mean, you should ask a very, very good question, which is, there are lots of rocks laying around in Switzerland. They're all over the place. They're very cheap. Why do you have to go out and build rocks for 4,000, 5,000 Swiss francs a shot? That's pretty stupid. That's like, get into trouble for that. Now, the reason why we do it is because this object, when it's rolling, the gyroscopic forces will put it up on its axis. And then you're going to have a nice footprint all the time. You're going to have the same impact geometry, right? We're always getting these smooth faces, or we hope we're getting these smooth faces when we do the experiments. That's why these wheels are for us extremely important, because we take away the shape effects in our full-scale experiments. That's why we do it. And here you have something, it's also the same. Be careful about the shapes of the objects that you put in when you try to measure these things, when you try to measure impact pressures. It makes a difference. Okay, now let's do something. What we can do is we can go back and we can take this force on the half and we could integrate it. And we can get the average force over time, right? And when we do that, we say we're not interested in the exact force at every particular location. We just want the mean force. Okay? And that, when you do that, what it looks like is that you have these shock forces from this pileup. Remember the story that I'm trying to equate. The avalanche comes, it hits the wall, it builds up these wedges, and then the mass flows around it. After the wedge is built up, the pileup force goes to zero. Right? At the beginning, when we're piling the most mass up at that little point, the force is the largest because the breaking distance and the amount of mass that we're stopping is the largest. Right? That's just the integration. Well, look at these times. It's about a second. Right? Second. Probably, I have no idea what they are. Could be half a second, could be 2 seconds. Depends upon whether you believe in the Spitzenforschung, or you believe in the pyramid model, or what kind of model that you have, right? Now, what you could do is you could say, okay, this is my pressure. I have a shock pressure. And what I'm going to do is I'm going to apply this pressure to the structure. And what I'm going to do is I'm going to calculate the bending moment to know if this moment is large enough to knock over the structure. Is that right? I mean, this is, right? That's what people do. Is it right? No, it's not. It's just to say that we can find the loading shape and the loading time. No. The reason why it's not right is the following. If you have a static load and you apply that to the structure, right, then the static load becomes the internal force in your structure. And I depict that with the spring, right? You have a load, you compress the spring. You use the spring to determine what the force is, right? Fine. Now, when you have an impulsive loading and you have a very short duration load, it determines what the mass, it's a function of what the mass is. So I look at, you want to know about this, don't you, Peter, what the tree is doing, right? But you have this mass. If this force is very short, if the duration time is very short and impulsive, what's going to happen is the mass is not going to move. You have to move, you have to overcome the inertial forces in your system in order to compress the spring, right? So it could be that you hit the object and nothing happens. The force doesn't, it just says, I'm not moving, I'm too heavy, my mass is too big. And therefore you have very, very small forces on your structure. It could be the other way around. It could be that you hit this thing at exactly the frequency where this mass begins to move, and it compresses the spring to an even greater distance. That's bad news, because that means that your force is going to be much higher from that loading. All right? And trees are really, really interesting things, because trees have these very, very low eigenfrequencies. The relationship between the movement and the mass is they swing very, very slowly. What the engineers do is they have what they call shock and response spectra, and they have what they call dynamic magnification factors. And what the dynamic magnification factor does is it tells you the factor that you multiply to this load to get the right internal force. So if you have here a triangular loading, and remember that's what we have sort of, we have this wedge piling up, it comes in, it's over, and it decreases over time. This dynamic magnification factor starts at 0, meaning you could have cases where the avalanche hits this thing and doesn't do anything. The internal forces, the moments are 0. You could have, on the other case, you could have cases where this dynamic magnification factor reaches the value of 2, meaning that you have double the force that on your, right? Now, why do I say this? Because when Stefan Margaret comes into your office and says, Perry, I had an avalanche, and I measured my forces at 10 kilopascal, what is he talking about? Well, is he talking about the external force, or is he talking about the internal force? Well, he's talking about the internal force. He's talking about the one that's breaking the structure. So what's happening is that this 10 kilopascal that he's talking about, it has to go through this filter, right? It could be 0, it could be 2. So we really don't know too much about this relationship between what the internal force is breaking a structure and the external force that is coming from the avalanche. Now, what is this ratio here? Well, this ratio is the time of the duration to the eigenperiod of the structure. Now, trees are really nice because what they do is they have very long periods. They swing back and forth. So an avalanche coming in that exerts a rather pulse is down here. So your dynamic magnification factors appear to be down here. I can't prove this, but you guys should prove this, Peter and Alex. This would be nice. On other cases, and you can have these pylons. Steel is not nice. I don't know what the eigenfrequency of the pylon is. It's about what?
This is less than 24 years.
Yeah. But you have to know that, because otherwise you're going to be in it. Below 10 hertz, yeah. But it's way. But you can get away. It's going to shift everything up in this direction. Okay. Now, this is some avalanches that I was. We're getting as much destruction as we possibly can. You can think, well, who cares about all of that? That's getting into this details and academia. And just give me the force, give me the pressure formula that I want. It turns out that what happens is, because you have to go through this filter, if you want to determine what, for example, the forces are on these structures, you have to be very careful. You have to know that exactly on these trees. You have to know these relationships between mass and internal stiffness. Otherwise, you can't calculate these things with an accuracy that I can calibrate a simulation program. Okay? So we're going to finish up with the last part of the talk. And I told you what we did. So the story is that the first thing that we did was we had an obstacle, and then we piled it up all in a straight line, and we let the mass come through. The next thing is we piled it up in a pyramid or in a triangle, and we sort of forgot about what happens to this mass that moves around the side. Right? Can't forget that. It does something. Now, you can invoke the same principle. You can invoke the work-energy theorem, right? It's this mass breaks out here, and these forces are carried to the obstacle by shear. Depending upon how this process happens, you're going to get larger or smaller forces acting on the obstacle in a region caused by this zone outside the avalanche. This material, because this mass is now, it has to move. It doesn't stay there. It doesn't pile up. It gets deflected. And as it's deflected into the flow, it causes problems. right? And the degree of those problems and the degree that the avalanche can accommodate those, that mass in this zone is a big problem. Sometimes it can do it very nicely. You don't notice anything. Sometimes it can't. If the density ratios are such, it tries to get this mass in here, causes all sorts of, it breaks the mass. The breaking distances then become very, very short, okay? So what happens then is that you get the same things. You get this behavior where, dependent upon what kind of density ratios and compaction and breaking distances that you have on this thing, you're going to get this very correct idea that these forces can go up to a very, very large, even if the avalanche is moving very, very slowly. And don't think that this thing can happen just at one place. It can happen in different ways everywhere on the avalanche, for example, in the depth, right? So you certainly would expect that you're going to have a density or a pressure distribution over the depth of the avalanche. So the last thing I want to say, use the work energy theorem. These forces are going to be large from this type of jamming. The duration of these forces, it's not going to be like the pileup that comes and then goes. It's not like the shock. What's going to happen is that you can get into a steady state where these breaking distances are then constant. So they're very long-acting forces. And Peter, yes, they are enough to knock down a tree. And I think the trees have a problem with this one, okay? And they're not, just like when you use the forces all the time, they're not going to be, when you calculate these things all the time, they're not going to be constant at a particular place on your object. They're going to be concentrated on the boundaries, on the edges of your object. But Stefan knows this, similar to the case, you know, when engineers design avalanche defense structures, what they do is they always strengthen the defense structures on the outside, on the outer edges. And the reason for that is this type of effect. That when the snow begins to creep around the object, the forces on the boundaries become very, very large. So we see similar effects. Okay, so just to stop, it's about 45 minutes now. To calculate, I want to indoctrinate you. Calculate the breaking distance. If you have a method, anybody says, hey, I have a method, I have a theory, go to the core, ask them what the breaking distance is and how they calculate it. It's not easy, right? This is why when you go to a geomechanics conference, everybody is talking to each other at the beginning, and at the end of the conference, they hit each other, because there are just so many different ways that you can do that, right? This is, right? It's not easy. Inertial forces, the idea that masses, that you have to take into the mass of your structure, this becomes important, right? All of these beautiful Swiss chalets, they're blocky, they're mass. That's probably the architecture is probably what's saving a lot of these houses, that they're so clunky and here's I would say right now, no practical engineering tools, calculation methods for real snow avalanche structural engineering problems. I don't think that those exist right now. And one of the things that we're doing with RAMs is to try to put in some better calculation tools for the practitioners based on a lot of what we're doing with these breaking distances, so that at least the engineers would have a transparent method of making decisions about what forces they want on their object. And to interpret measurements. Simple, clean impact geometries would be a help. Measure both the internal and external forces. Right? One of the reasons why that's important is because the French, for example, measure the internal, we measure the external. But when you're talking and communicating to people, then I think that you have to be able to understand what the difference is between these internal and external forces. And it's certainly possible now with these sensors of Van Green that you can put them in an avalanche and you can begin to measure decelerations, right? So that would be possible. So if you had a combination of all these three measurements, where you get the deceleration of the snow, which is the force acting on the object, and then you would measure the different forces in the object, then I think that you would have a complete picture of what is a very, very difficult problem. Okay, that's what I wanted to state. That's it. All right? Finished.